Hello and welcome back. This is a continuation of a series called Implementing Real-Time Object Detector using Yolo version 3. This is the second installment in that series. So in this video we'll actually start to implement the Yolo version 3 network from scratch using the configuration file. But if you have not watched the previous video where I have explained the theory behind the network and how it makes detections, I mentioned a lot of things directly from the research paper. So if you have not watched that video, you might not get a lot of things that I'm going to be explaining here. So it's highly recommended that you go and watch that first. With that said, let's get started. So I have a lot of files here, so I'll just quickly explain what all of these are. So pycache is just a cache file, so you don't have to worry about that. Now this CFG folder contains the configuration file of various Yolo networks. So these are available online for free on the author's site. So we're going to be building Yolo version 3. This is the full version of the network. There's Tiny Yolo and Yolo VOC and different versions of Yolo, but we'll implement this Yolo version 3. Let me just quickly open this and you'll see it contains a lot of information about the network. Actually, it contains all the information about the network. So this is all you need to build the network. So as you can see, it has a lot of layers, more than 100. And so the first few lines contains all of the information about the layer, the batch size, subdivisions, channels, and all of that, all of those things. Now the network actually starts from here. So the layer is mentioned in brackets, the type of layer, convolution, and then it is followed by all of these properties, and then the next layer, and so on. So we'll use this file to implement our network. So we'll first parse this file in a format that is convenient for us to implement in pytorch, and then we'll actually implement the network. So this is a configuration file, and this is what is meant by implementing networks using a configuration file. So you can use various languages to implement the network if you have the configuration file. Now there are two other files here, actually a lot of files here. So the first code file is DN model. I have named it after darknet model because we are going to be building a darknet model, a replica of that using pytorch, and then a util file that contains some of the utility functions that we are going to be using. So I'll just quickly skim over it. I won't discuss it in detail because these are some most commonly used computer vision algorithms, so you don't have to know all of those in detail in order to understand Yolo version 3. So these are the code files for now. We'll add more code files in upcoming videos. And then the data is coco.names and voc.names. These file contains the names of the classes. We're going to be using coco.names because we are working on coco dataset. And this is the pre-trained weight, again available on the internet, pre-trained Yolo version 3 weights trained on coco dataset. So it is available on the internet, and I have the link in the description, so you can download it from there. Now back to the first code file, that is DN model, darknet model. So I've imported a lot of things: torch, functional, numpy, opencv, and util file, which is here. So the first two classes, the dummy layer and detector, I'll come back to them later on. Let's just first start from here. Construct CFG. So well, as the description of the function says, it builds the network block using configuration file. So basically we pre-process the configuration file here, generate a form that is easy to manipulate using pytorch. That is what written here. So it takes input, the configuration file. So it's straightforward, you can just read it here. So we first read the file, and then we split the lines. Then we ignore the lines that are either comments or they have no values. And then we strip the spaces from the lines. Now I have a list and a dictionary. So a dictionary will contain a network block, and then the network blocks will, well, as the name suggests, it will contain a lot of network blocks to store different kinds of layers. So we'll iterate over the file. Then whenever we encounter this opening bracket here, so we'll realize that this is a starting of a new layer. So if we are already working on a previous layer, we'll just append that in network blocks, and then we'll empty this network block so that we can store the next layer. And well, all of them are intuitive now. But if we don't encounter this starting brace, we'll realize that we are in the middle of execution of some previous layer. So we'll split the lines in two parts, separated using an equal to sign. So this is the value after the sign equals, and before that is your entity. Here we have separated them using the split function. And then again, just get rid of the space from entity and value, and then in the network block you just append that. And finally in the network blocks you append the network block. That's it. So this is our function that will construct the configuration file. So before moving on, because it's a very large file, let's just test this function. So here I've written a test case. So let me just comment this model test out so that we can just test the configuration file. Let me just run this. So as you can see, it's a lot. So it basically is the list of all networks in form of dictionaries, a list of dictionaries, and in this way we can easily manipulate the layers. So again, as you can see, the first dictionary contains the information about the network, not the layers, and it is straightforward because the YOLO configuration file, the first part, contains all the information about the network. Let me just get rid of this output, and so you can see it contains all the information about the network, the net parameter. Alright, so we have tested this out. Let me just again comment this because we won't test again. It's working fine. And later on we'll test this part. Alright, let me just quickly, let me just proceed. There's another function called built network, and it will take the output of the configuration file, the network blocks. Alright, so as I've already mentioned, the first list contains the information, so I have named it darknet info, DN info. And the modules create modules from the network blocks, so we'll store all those modules in nn.module list. It is a part of pytorch, so module list can contain different modules. Now channels is equal to 3 means basically we are working on RGB image, so those images have 3 channels. And then filter tracker, it tracks the number of filters used in different layers. Alright, so then we enumerate the network blocks and we'll just iterate over that. So I have set sec module is equal to nn.sequential, so it will contain one layer, the sequential layer. So if x.type is equals to convolution, so as we have seen in the output, we always have type of layers. So so we stored this parameter in a entity called type, as you can see up here. In this way we can know about the kind of layer that we are working on. So if type is equals to convolution, so we know that the convolution layer has all these entities: filters, pad, size, and stride. So just separate them out. Now if there is padding, then calculate that, otherwise set padding to 0. Then activation, so again if there is batch normalization, just try it out, otherwise set batch normalization to 0 and bias to true. And then straightforward, let's just call nn.con2d and use all of these information, channels, filters, kernel size, and stride, to build this model. And now sec module.add module will add to that convolution and the index, that is I. This is the syntax of add module function. It takes a name and the module that you want to add. So we'll add this con module and that is the name. Okay, now if bn, if batch normalization exists, we'll add batch normalization. And if activation is of leaky type, which means leaky relu, so we'll add an activation module. So in this way we have added all the modules if they exist. So now our sec module will have a sequential layer containing convolution, batch normalization, and leaky relu if they exist. Now there is another case if this is an upsample layer. So upsample is basically a transpose convolution. Basically it upsample. So whenever you perform convolution, the size of the height and width basically decrease. Now upsample increases that. So we'll use upsample of scale factor 2 and the mode is bilinear. So by default bilinear mode is used, and there is a lot of mathematical details about bilinear, but it is a part of advanced image analysis, so I won't go there. Now again sec module.add upsample. Now this is something new. If the type of the layer is route layer. Now what is route layer? So if you watched the previous video, we had seen different kinds of layers, and one of them was the route layer, which basically concatenates the output of some previous layer into this layer. So if you don't remember this, just go and watch previous video, that part. So it is just like ResNets. In ResNets we add the outputs, but in the route layers we just concatenate them. So let me just quickly show you the route layer. So this is a route layer, so it mentions which layers you have to add. So -4 means 4th previous layer. Again, there might be another route layer. Here it is, again -4. Now sometimes it has to concatenate multiple layers, so it has previous layer and 36th layer. So as you can see, it's not a very straightforward operations. Layer might be mentioned in this form with a negative sign, which means the starting from this layer to go these many layers backward, or directly the layer number might be mentioned. So we have to take care of this. So that's why we have some operations here. So first of all, if the type is route, then we'll perform these operations. So we'll just first of all extract the layers if there is one or more. Now generally there are only two cases, if there is one layer or there are two layers. So in this case there are two layers, and in some cases there are only one layer. There is only one layer. So we can be sure that there is at least one layer in the route layer. So the start is, we can just directly say the 0th index of the layers, and then we'll try this and we'll check that if there exists another layer. If it doesn't, then we'll set the end to 0. Now if start is greater than 0, so there are two possibilities, that it is greater than 0, the layer number is mentioned, otherwise it will be negative. So if it is greater than 0, then subtract the current index from it to make it negative, and do the same with end. And here is where the dummy layer is used. So in the beginning of this video I mentioned that these two layers, I'll discuss them later on. So here is the dummy layer. The dummy layer is basically a part of an n.dot module, so it does not do anything, but it's just there to be a part of that network. It just inherits from an n.dot module, because the routing layer does not do anything, it just concatenates the previous layers. So that's why we'll use dummy layer here to just assign a network module, and it does nothing right now. Okay, so we'll just add this module here. So if end is less than 0, which means there is a second index, so we'll just add the number of filters, the final output will have. Otherwise the number of filters will be equal to basically the start, I plus start. So this filter tracker, basically I mentioned it tracks the number of filters in each layer, so we'll just track that. Now if the layer is of shortcut type, and by the way, if you don't get this routing layer, just go and read about it a lot, because you have to build up intuition about this. Just read this code again and again and try to decode what it does on your own. You'll learn a lot, because this is a new kind of layer, so a lot of people don't know about it. I also came across this when I was reading about Yolo version 3. So otherwise everything else is just straightforward. Now the next part is the shortcut layer. Shortcut layer basically means residual layer. Again we'll use dummy layer because it does not do anything here. It will just add the output. Well, it does something, but in the net class. This is just parsing. We have not yet started any operation here, so that's why again we'll use dummy layer, and here we'll just add module. And the final layer is Yolo layer. So there are three detections, which is the detector layer. Again, in the previous video I mentioned it is one of the kinds of layers. So it is a detector layer, so it detects. So there will be three Yolo layers. Again, let me just show you. So as you can see on the right here, there are three Yolo layers. So this is the first scale. The anchor box says masks, heights and widths, the anchor boxes, and again these three scales. Alright, so let's see what it does. So first of all, it will just extract the anchors. So anchors are all same because there are 9 anchor boxes. So there are 9 heights and widths. So first you extract the anchors and then convert them to integer. And then mask. What is mask? Mask basically means that, well, each cell makes 3 detections. So it means each cell needs 3 anchor boxes. So out of these 9, which anchor boxes to use? Well, the mask will decide that. So we'll use 0, 1 and 2 index layers. So 0, 1 and 2 here. And each Yolo layer will use different masks. So let me just show you here. So it will use 3, 4 and 5 like that. All of them will use different masks. So first extract all the anchors and then extract the mask, and then again convert the mask to integers, and then group the height and widths of the anchors, and then select only those anchors that are mentioned in the masks. And finally use the detector layer. Here is where the detector layer is used. So again, detector layer just takes one parameter, that is the anchors. So we'll initialize that. So we have initialized this, and we'll add the module, and modules will append the sequential module list, that is add module list. And then again we'll add filters to filter tracker. Channels is equal to number of filters, that's it. And then we'll return dn info and these modules. We have successfully parsed here. Again, you might test this function. I have not tested this function out because we have tested this configuration file. So this is very similar to that configuration file. First convert this configuration into a list of dictionary so that we can easily parse that. So I'll just minimize this function here, and then in the build network we'll use that semi-parsed state to build module lists, and then we'll return the information and the modules. Let me just minimize this again. Now finally we come to the net class, which will do all the operation. So the constructor takes the configuration file, that's it, and then we'll first construct the network blocks using configuration file, and then we have dninfo and self module list from build network. So you use this function, it returns info and modules. This header and scene variables will be used later on when we make detections. Alright, so forward function. So each network has forward function in pytorch. So it will take x, that is the input, and the CUDA variable, which is either set to true or false, which signifies whether CUDA has to be used or not. Now detections will contain number of detections or the list of detections that are made. So modules will start from self.net blocks, and it starts from index 1 because the first index contains the information about the network, that is dninfo, and the layer outputs, the output of each layer. We have to store the output of each layer because routing and shortcut layers use the output of previous layers. Alright, now this variable return output is equal to 0, which signifies whether we have written any output or not. So if we have not written any output, it will store 0. So right now it stores 0. Now let's iterate through each module. So if module type is convolution or upsample, both of them are a kind of convolution operation. So we'll just perform that operation using module list of that module, and then store the output in the layer outputs of this particular index. Now, if there is a route layer, so we'll first access the layers, all the layers, and then convert them to integer. Now again, if the layer's number is greater than 0, which means it is mentioning the other layer number is greater than 0, we'll perform the same operation that we did in the CFG file operation. We'll subtract the index from it. Okay, if the length of layer is 1, which means there is only one routing layer, we'll just quickly append that in layer outputs. Otherwise, if layer number is more than that, then we'll check whether the second layer is greater than 0, perform the same operation, and then there are two mappings, one from the start layer and from the end layer, and then we'll finally concatenate them across the width, and then we will store that output. Alright, now a shortcut layer. So as I've already mentioned in the comments, it is essentially the residue of ResNet. So we'll basically add the output from stores the layer from which we have to add the output to the previous layer, and then we'll just append that in layer outputs. Now here is the detection layer. There are three detection layers. So this will process all three of those detection layers. So if the module type is Yolo, which means it is a detection layer, we'll first extract the anchors. We'll get the input dimension that is in the dninfo, that is the height of the input, and the number of classes that is again in the modules. Now this is the input data, and comment all of these things, because in order to understand what's going on here, we'll have to look at the output, the shapes. Alright, so in this layer, first of all, what we do is we take the output of the previous layer, that is x.data, the output of the previous layer, and then we'll convert them into 2D. As you already seen in the previous video, the output before the detection layer has 4 dimensions, and we convert them to 2 dimensions so that it is easier to append all the outputs together and perform operations on all of them together. So here we will see how it happens. So the size before the transform operation and the size after the transform operation, and this transform output is a function in the utility file, that is util file. What it does is it basically takes this data from the data in the 4D format, and then it converts into 2D, which is so grids, the total number of grids, that is height into width, times the bounding box attributes, which is 85 in this case, as I've already mentioned in previous video. One more thing about the transform output I'd like to mention is, let me just go to the return here. I won't explain this function because there are a lot of operations going on here. You can just directly dry run this and try to debug this on your own, and you'll see that it's basically converting the size and performing some operations that are given in the research paper, transforming the outputs using some formulas in the research paper that I've already mentioned in the previous video. Alright, so finally, I just wanted to know that if there are no detection made, the return prediction will contain an integer value, 0. Otherwise, it will contain the detections in the form of grids into bounding box attributes. So if it is an integer, just continue it because there have been no detection made. Now, if not written outputs, there have been no outputs written already, set detections equal to x and return outputs equal to 1, so that we know that there have been some previous outputs. So now we can concatenate this output to the previous output. So detections will be equal to torch.concatenate detections and x across the width. The layer output won't change because this has not performed any operation, so the layer output of this layer will remain as same as the previous layer. So there's just that. Now this is just a precaution. This try and accept block is just a precaution when there are no detections. So if return detections. If there is no detection, then return 0. Alright, so this is our network. Now what we can do is we have to load the weights. Now this part of code seems really daunting, but it's not. It's really easy once you understand what's happening, and it will just happen over and over again. First of all, it will take the input as the weight file. As you have seen in the beginning, I have said that we'll use the header file later on. Is an integer tensor that will contain first 4 values. In the weights file, the first 4 values contain the major version number, minor version number, subversion number, and the images seen. So we won't necessarily use this information, but we have to store it somewhere so that we can just move forward. So first we'll read from the file 5 values, then store the header and the scene, images seen. Now finally convert the data type to float 32, and then we'll start a tracker. So tracker will track the number of terms that we have already seen. Loop for different modules in self.module list. Now if the module type is convolution, check whether there is a batch normalization or not, otherwise set batch normalization to 0. Now if there is no batch normalization, the con part will be the first part of the model, as we have already stored it that way. First convolution part, then the batch normalization, then activation. So the 0th part of the model, the 0th index, will contain the con part. But if there is batch normalization, we'll have to add that. So in the comment I have mentioned how the weights are stored in the weight file. So first of all, the bias of batch normalization, then the weights of batch normalization, then the running mean and the running variance of the batch normalization. So in this way, batch normalizations are stored. So bn part is the second index of the model. So let's count the number of bias terms. So bn part dot bias dot numel returns the number of parameters in the bias. That function comes really handy. So let's just convert from numpy to torch tensor the weight tracker to tracker plus bias count. Now increment tracker by bias count. Repeat the same operation for the weights of bn weights, the running mean, and the running variance. So all of these are same operations. So as I've already said, it looks really daunting, but it's really simple. Now finally, we'll just reshape these to the desired shape if there is some discrepancy. These are just precautions to be made, right? So if the weights are not stored in the way that you want, so we can just quickly just convert them to the way we want. It will change the shape of the bn bias to the bias of the bn part if they are not same. Do the same with the weights, running mean, and variance. That's it. Now we'll copy that into the network. So bn part bias dot data, copy the bn bias, and then the same thing with bn part weight, bn part running mean, and average. Alright, so if we had to perform batch normalization, then we just do all of these operations. Otherwise, again, count the bias, extract the bias, and add that to tracker. View that as the con bias, and then copy it. And then finally, let's move to con part, the weights of the convolution part. Again, perform the same operation and then copy it. So that's it. These are all the weights that we need. There are no weights for routing layers or shortcut layer because they don't perform any other operation or convolution. They don't need weights. They're just adding or concatenating. This is our weight file. Alright. Now let's test the entire network and the output with it. So all of these comments will be clear. Size transform, because this is the only thing that needs to be understood, the size transformation. Otherwise everything else is straightforward. You'll just look at the code and you'll get it. It's just that the code is really long, but reading and understanding such a large code base will always be a good practice. So let's finally move to testing our layers. Now number of classes is 80. That is the Cocoa dataset. We already know that. Now load classes. This is a function in the utility again. I won't mention it. It basically loads the classes from cocoa.names. And then initialize by passing in the configuration file, and then we'll call the loads weight function and pass the weights that I already have it here now loaded, and then we'll print network loaded. We'll make some test data of this size. The batch size is 1, and 3 times this is the number of channels, 256 and 256 is the size, height, and width of the image. That's it. And let's just get rid of this test data, and the test output will be, we'll pass this data into the model, and we will not use CUDA, and then we'll print the size of the output to see how many detections that we have made. Okay, so network's loaded, and So first of all, let's just ignore this warning. It is just because upsampling has been deprecated, but I have checked it on the internet. There is no problem while using it, so we can use it. So just ignore that for now, and let's try to deduce what's happening here. So we have printed two things: size before the transform, size after the transform. So as you can see here, the size before the transform was something like this, and it is converted into 2D, so from 3D to 2D. So it is basically the number of detections made, means the grid size, and then into the class attributes. The 80 is the class probability. First four values are the center coordinates x and y, and the height and width, and then objectness confidence. It is all mentioned in the previous video. Just go and watch it if you don't get it. I've mentioned all of this in detail. Again, this is the second scale. It is again converted into some value times 85, and then the third scale, some value times 85. Now the final size that I have printed here is the size of the output, this part. So if you will just analyze it carefully, you'll realize that the size of the output is basically the concatenation of all these three. Size after transform: 192 plus 768 plus 3072, we get 4032. So these are the total number of detections made, and then we'll perform the operations, get down to the real detections. These are all including multiple detections and all of these things. We'll use NMS and all of these things when we will detect from an image or from a video. So but here we have built the entire network and use the pre-trained weights of Yolo version 3. So this is a big deal. We have implemented the Yolo version 3 network from scratch. If you have not understood something, don't worry, because the first time I tried to implement it, I read a lot of articles about it. A lot of things were not clear to me. So just experiment with this. Try to print all of the things and try to just decode the network, and then you'll get it. So this was it for this video. We have implemented the network from scratch, try to understand it, and in the next one we'll use this network to detect objects from images, and after that we'll use the same network to detect objects from videos, and all of that will be in real time. So thanks for watching, and stay tuned for the next one.